Okay guys, today we're gonna learn chapter 3 for KRD Jan, which is rate law and stoichiometry. I bet all of you have studied this during your high school, right?
Yes.
So in this chapter we're gonna go deeper into rate law and stoichiometry. Okay, firstly we're gonna consider this reaction, the red one and the blue one. The red one will be the stoichiometric coefficient, and the blue one is the species involved in the reaction. Understand?
Yes.
Okay. The rate law equation is given by negative RA equals to KA CA to the power of alpha and CB to the power of beta. Negative RA is the rate law, K is the coefficient, C is the concentration, alpha and beta is the order of reaction. Okay, I'm gonna explain this later. Basically, rate law can be divided into two parts, elementary and non-elementary. Okay, if we arrange the equation, we're gonna get negative RB equals to dA times negative RA.
So that is the reaction with respect to concentration B, is it?
Yeah. If we use B and A, we can get the rate law of B by using this equation.
Okay.
You understand?
Yes.
Alright, we continue. Okay, reaction order. As I said just now, alpha and beta is the reaction order. Alpha is the reaction order for species A, and beta is the reaction order for species B. Okay, and we can calculate the overall reaction order, which is alpha plus with beta. Then we will get overall reaction order. And for your information, reaction order must be determined experimentally. What I mean experimentally is that we must determine it in the lab using some experiment, doing some calculation, and then we can get the reaction order. Okay. Alright. And then I'm gonna skip this. Okay. For this part, there is first order, second order, and third order. As you can see, for the first order, the power of C is 1. For the second order, the power of C will be 2, and so on. For 3, 4, 5. Okay. This is elementary rate law and non-elementary rate law. For the elementary rate law, the stoichiometric coefficient is equals to individual reaction order of each method. For example, for the stoichiometric coefficient is 1, B is 1, C is 1, and D also is 1. So we can assume that as the elementary rate law. And for for a non-elementary rate law, we can divide it into free radicals, solid catalyst reaction, and non-elementary rate law is much more complex than elementary rate law. Okay. And then for the reversible reaction, the net rate of formation of any species is equals to rate of forward plus rate of reverse.
So the net rate will be 0, is it?
Yeah, and at equilibrium the rate net will be equals to 0. Okay. For the rate constant and activation energy, K will strongly depend on temperature. As you all know, for Arrhenius law, you know right, Arrhenius law, K is depending on the temperature. So we can find activation energy using this equation. This is the activation energy, and we can, after we solve this equation, we can find the activation energy. Okay, I will show you how to find the activation energy. Okay. We can make a graph of log K versus 1 over T, and then from the slope, we can get the slope is equal to negative E over R, which is gas constant, and then from that slope you can determine the value of activation energy. Okay. Okay. For the first chapter, for the first part, which is rate law, I've done I've explained you some basic information, and then for this second part, which is stoichiometry. Okay, stoichiometry. We need to express concentration as a function of conversion in order to carry out calculations. Stoichiometry, what does it tell us? Basically, stoichiometry can tell us many things. For example, a complicated stoichiometry usually indicates multiple reactions. For example, A will become 1.45 R plus 0.8 is X. So, in this section, there is a complicated stoichiometry. So, it indicates the multiple reaction. Okay, the next one you can read yourself in the room. Okay. Basically, in stoichiometry, we must construct a stoichiometric table. What is stoichiometric table? Stoichiometric table will look like this. This will be the species involved in the reaction. This is the symbol that we use for the species and its initial concentration, the change in concentration, and the remaining in the concentration of that species. Okay. For the species A, we use symbol A. The initial concentration is Na0, and the change in concentration is minus Na0 times the X. X is the what we call how many percent that have changed. Yeah, in the reaction, and the remaining. Okay, for the B, C, and D, you can study it yourself at the room. Okay, and then stoichiometry for flow system. This is for the batch system. Okay, for the batch system, and this is for the flow system. The only difference for the flow system and the batch system is that the batch system use Na0 for the concentration, where the flow system use Fa0. That is the only difference. Okay. And then I think that's all for me. Thank you for the attention, and see you guys around. Class, for the flow system, constant volume. For this part, we can calculate the concentration by using this equation. And concentration can be determined from the flow rate divided with the volumetric flow rate, and we can get the concentration. Okay, and then for liquid phase system, we must know that no phase change, so there will be a constant volume. For gas phase system, the above statement is not true, because we need to account for the volume expansion. Alright, so we have a volume change reflection, and this will occur when the system does not have an equal number of product and reactant. Usually, it evolves in a gas phase system. For example, nitrogen with hydrogen. So we're gonna take account the expansion of the volume for the reaction. So we need to calculate the expansion factor, which is change in total numbers of moles from complete combustion will be divided with the total number of moles fed to the reactor. Okay, so you can see that at complete combustion, the expansion factor will equals to this. Okay, class. And then for batch system and for the flow system, for the batch system, we use this equation for the volume, and for flow system, we use this equation to find the concentration. Basically, you can derive this equation yourself at home and submit to me as the assignment tomorrow. Okay, this is all for today. Thank you, class.